Okay, we're going to continue on here. Going to wrap up 16 is where we're at. Then we'll roll into 7. Then we'll roll out of here for today. So obviously on 16 here, we talk about thermodynamics. And we got into really sort of Gibbs free energy, which after using K for a lot here is a different letter. So that is delta G is the change in Gibbs free energy. And we actually saw a couple of different sort of formulas that use this. We had our delta G naught is equal to delta H minus T delta S. Again, that is our free energy. Usually in kilojoules is sort of how it's usually given. That's our enthalpy, which is also usually in kilojoules. That's our temperature, which is in Kelvin. And lastly, that is our entropy, which is in joules. So as we talked about, again, you definitely want to watch out sort of units as you're using these equations. Otherwise, you'll find yourself sort of off by a factor of 1,000, which you definitely don't want to be. We can use Gibbs free energy to determine whether or not a reaction will be spontaneous based on sort of the sign of delta G. And if delta G is negative, usually that means the way the reaction is written, it is going to be spontaneous. And you would expect products to be formed in that particular reaction. If the delta G is positive, it'll be non-spontaneous the way it's written. And again, you wouldn't expect, obviously, products to be made. But if you did sort of reverse the reaction, it would become spontaneous because, again, your reactants and products basically will kind of swap places. Another way that we could calculate delta G is pretty much like all other sort of thermodynamic values. We take our products minus our reactants. We can go to a table and look up what's sometimes referred to as the delta G of formation for these substances. And again, these are values that you could find in a table. You want to make sure you got the right state for these guys and really do our products minus our reactants, which, as we talked about a number of times, is essentially our sort of final state minus our initial state when we're dealing with obviously a chemical reaction, and that's a very common way. So which sort of formula should you use, as we talked about as well? Again, it's really based on the information given to you. So if you're pretty much just given the reaction and nothing else, and you need to calculate delta G, then that's definitely products minus reactants, go to the table. If you are given the delta H or the delta S or have some information to be able to calculate both of those things relatively easy, then you could use obviously the one that has the H and the S in it, and those are sort of your best options. Any questions on any of that stuff there? All right, so let's continue on then, and let's talk about actually Gibbs free energy and the equilibrium constant, because we can't leave K out for too long, otherwise we're in the wrong class, I suppose. And this does bring up a couple other sort of formulas that do have our delta G in it. And this formula right here is delta G is equal to delta G naught plus RT natural log of Q. So these are a couple of different delta G's, and the way you could kind of think about these are, again, when you see sort of the little knot above like a delta G or a delta H or a delta S, that usually means in most cases that's under standard conditions, which again means the temperature is like 25 degrees Celsius. If you're dealing with any gases, their pressures are 1 atmosphere. If you're dealing with concentrations, it's usually 1 molar. These are sort of what we associate as sort of standard values, and these are standard conditions. And these are really the values that you would find like in a table that you go look up all those values when do like products minus reactants. This delta G you could kind of think of as sort of non-standard conditions. So that would mean obviously one of those things is not taking place. So the temperature maybe is not 25 degrees. Again, if you're dealing with pressures, maybe they're not all 1 atmosphere. If you're dealing with concentrations, then again, maybe they're not all 1 molar. So That's sort of the difference between those two delta G's, one sort of non-standard conditions, one sort of standard conditions. The rest of the guys in this formula is pretty much kind of the same. R, though, is the gas constant that does involve energy. So the 8.314 version of it, not the 0.08206. Temperature here, like most things, needs to be in Kelvin. And our natural log Q, Q is still the reaction quotient, which is, again, basically the concentration of our products divided by the concentration of our reactants. So remember that basically Q is calculated the same way as we do equilibrium constant. Again, we still use coefficients as the exponents, and everything's the same. Now, if you happen to be at equilibrium, the top equation, a couple of those things ends up being sort of zeros. Actually, the non-standard delta G will equal 0. And if you are at equilibrium, we're no longer calculating Q, we would be calculating the equilibrium constant. And if you substitute that in, you do get this equation here, which is the delta G naught is equal to minus RT natural log of K. So again, this sort of opens up multitude of sort of formulas that involve sort of delta G. So as we just saw before, you can take delta G of a reaction, delta G of our products minus the delta G of our reactants. We could also do the delta G is equal to delta H minus RT delta S. So again, the same sort of rules apply. As I mentioned before, just the equation, roll with that one. Again, if you have H and S, you should roll with that. If you have anything to do with the equilibrium constant, either it's given to you or you're looking to find it, then you should roll with the bottom one. And lastly, if you got some type of non-standard conditions, then you should obviously roll with the top one. So again, best way to kind of approach it is based on the information given to you in the problem as to which of those formulas that have delta G in it would be good. By the way, in some of the problems, this delta G naught is given to you, and in some cases, you may need to calculate it yourself, and you would calculate that delta G naught by doing this. Again, our products minus reactants is how you would get that delta G naught, which is just kind of the normal way. Looking up the values in the table. Again, in some problems, it may give it to you. In other cases, you may have to also calculate that one as well. Any questions on any of those there? Now we could look at this bottom equation and make some predictions based on what's going on. And for example, here, if we, the good news is if you still understand, obviously, equilibrium constant, that's still something that you could look at. Obviously here, if we had a large value for K, we would have a lot more products than reactants. And in order to have products than reactants, that would probably mean that this reaction has to actually happen and go to the product side. That would only probably occur with a negative delta G. So again, those two things are related to each other. Obviously, if you have a small K, that means that we do have more reactants than products at equilibrium. That would also imply that this reaction is probably not going anywhere, not really happening. Otherwise, we would have more products being made at this point. So because of that, we can make an assumption, obviously, that our delta G here would be a positive value. And if K is equal to 1, then delta G would equal 0, and the reactants and products are comparatively abundant. But again, products favored if we have a large K are a negative delta G, and vice versa there. If we have a small K and positive delta G, then reactants would be favored. So again, the nice thing about that, it has K, so you can kind of still think about K that way and get an idea as to what should happen. And what I mean by that, for example, if you were given delta G, and you had a positive value, you would expect if you were calculating K, it should be a small value. And if you're given delta G and it's a negative value, then when you go calculate K, it should be a larger value. And vice versa, if you have the K values given to you, then you should be able to predict whether or not you would have a positive or negative delta G if that is something you're calculating. Now, a couple of things about these two equations as well that sometimes it's commonly messed up by people, I think, is this top one. It is plus here. So a lot of people always want to subtract this one. So just remember that that is plus, and people also like to kind of forget the negative on this one. So just keep that in mind. Those kind of pluses and negatives sometimes throws people. All right, so why don't you give it a go here? Some delta G's from the table. Why don't you give it a go? Calculate the equilibrium constant for the following reaction. Okay, so let's take a look and see. So again here to help you decide, I'm looking for the equilibrium constant. So the equation that we just saw there is really the only one that has that in there. And I really remember that it doesn't matter what type of K it is, they're all the same. They're all equilibrium constants. So, the little subscript won't really matter here. In this case, we do have R always, and it is the gas constant that has that energy. We do need to convert this into Kelvin, so we'll add a 273 to it, going to give us 298. And in this particular case, they did not give us delta G, but we can go to the table here and calculate it. So this case, we would do our delta G of our products minus the delta G there of our reactants. So our products in this case is 3 times 0 kilojoules minus 2 times 163.4 kilojoules. And that's going to give us something like, looks like negative 326.8 kilojoules in this case. At this point here, we're going to put it into here. I am also going to multiply by 1,000 here. So I watch my units. The reason I'm going to do that is for my R, which is in joules, not kilojoules. So again, you do need to do that conversion. Otherwise, you're going to be off by obviously that factor of 1,000, which you do not want to do in this case, as you are also inversing or eing each side. We'll put our temperature in there, which is 298 natural log of K. So I'm just going to multiply these guys together and then divide it over to that side. So we'll take basically, we got there, 326, there it is, 326.8 times 1,000 negative. We'll divide it by basically negative 8.314 and divide it by 298. So that's going to give us that we got something like 131.90 is equal to the natural log of K. At that point, we do need to take the E of both sides. And again, the E is just going to get rid of the natural log on that side. And that will get us our K value in this case of about 1.9 times 10 to the 57 in this case here. It is a K value, which means obviously we don't need any type of units associated with it. First off, any questions on that there? The two values do make sense. We ended up with a negative delta G, which means this reaction should be spontaneous and should be heading towards the products, which means products should be favored. That would mean we would have more products than reactants, which should give us a larger value for K. And I would say that is a large value of K in that particular case. Any questions on that one there? All right, let's try another one here. Calculate the delta G naught for the following at 25 degrees. The KSP here is 1.7 times 10 to the minus 6. Okay, so let's take a look at this one. Once again, here we are given a KSP, which is going to send us to really the only one that's got, again, the equilibrium in it, which is the same one we just used there. And again, it doesn't matter which K value you use. In this case, we have that, we do have that, and we do have that. So we just need to plug this in here. So delta G naught will equal minus 8.314 joules per Kelvin per mole. Again, converting our 25 degrees into Kelvin to 98 when we add our 273 to it. Natural log of our KSP, which we do have here in this particular case. So putting those guys in, 8.314 times 298 times the natural log of 1.7 to the minus 6. And we don't want to forget the negative that's in the front there. And that's going to give us 32,914. The units here would be joules, are roughly 32.9 kilojoules, which is typically the units that delta G is given. First off, any questions on that there? Once again, when we look at sort of the values, they do sort of make sense. We have obviously here a small value for K, which is what we would expect with the KSP. And with that, that would mean that the reaction probably is not going to be so spontaneous, and reactants would be favored in this particular case, and we would expect a positive value for our delta G in this case. So again, if you forgot the negative there when you're doing the calculation, but understood that, you hopefully would catch it, because you should not have obviously a negative value, which is a small value of K. So those are things you want to watch out for. Questions on those two there? All right. I give this one a go here. Delta G naught for the reaction is 2.6 kilojoules per mole at 25 degrees. In one experiment, we have some initial pressures for H2, 4.26 atmospheres, I2, 0.024 atmospheres, and HI, 0.23 atmospheres. In this case, we want to calculate the delta G for this reaction and predict which way this reaction would head. All right, so take some time there and figure that out. Okay, so let's take a look. So in this case, a couple of things we want to look at. We obviously have a delta G not given to us, and we're looking for a delta G. So there's really only one sort of formula that deals with both of those. So that's the delta G is equal to delta G naught. That's a plus RT, natural log of Q. Here, this is really non-standard conditions because of the pressures here. Again, the pressures are not 1 atmosphere, which is what standard conditions would be. So that is really what's different here that makes you have to sort of figure out what the delta G will be with these non-standard pressures. So remember, when you kind of look it up in the tables, if it's something that's gases, it's assumed to be 1 atmosphere. So with that being said, we do obviously have here our delta G not given to us. We have R, which is again still that 8.314 joules per Kelvin per mole. Our temperature here is our 25, which converted to Kelvin is going to be 298. So at this point, we really need to calculate Q, and just a reminder again that Q is just like K. So we'll do our products, which in this case is going to be the pressure, and we do need to square it of HI because of the coefficient, just like normal. We're going to divide it by the partial pressure there of H2 times the partial pressure of I2 in this case. So we'll put in our numbers here, and it looks like we got 0.23 squared divided by 4.26 and 0.024 in this case. That's going to give us a Q value here of looks like something like 0.5174. Take it to a couple of digits, maybe. And that's really, again, everything that we got going on. We do need to also, once again, watch the units as this is kilojoules. Once again, this is joules. So we do need to do some type of conversion. Otherwise, again, you're going to be off. So like normal for me, I'm just going to multiply by 1,000 here and turn that into joules. So it'll match up good with my R value. A reminder as well that the R is 8.314 joules per Kelvin per mole. And we're going to do our 298 Kelvin. And maybe let's erase that there. So we got somewhere to go with that. And then we're going to natural log the Q that we just calculated there. That's our Q. So natural log of 0.51741. So we could clean up really everything on the right-hand side. So we'll go 2.6 times 1,000 to convert it to joules. Again, we're going to add, not subtract here. 8.314 times 298 times the natural log of 0.51741. And looks like we will end up with about 967. Once again, because I did that conversion, I'm going to be in joules in this case. Although delta G is usually given in kilojoules, so if you divide it by 1,000, 0.967 kilojoules if you want that way. First off, any questions on that calculation there? This is a positive delta G, which means that reactants in this case would be favored, as the reaction would not be heading to the product side because it is not negative. Right? Also means, obviously, if we calculated our equilibrium constant, we should end up probably with a smaller value for K if we got to that point. Any questions on that there? So again, if you got some type of condition, most of the times it's probably pressures or concentrations that are really not 1 atmosphere or 1 molar, then that's the equation that you need to use there. Again, temperature could also be not 25 degrees as well as another variable. Questions on any of that there? All right, that should wrap up this chapter. Okay, then we're going to continue on to chapter 17 and change gears a little bit more. In this chapter, it's all about sort of redox reactions, electrochemistry. We're going to talk about basic sort of oxidation reduction, what's going on. We're also going to talk about balancing equations in acidic and basic conditions. Again, depending on maybe who you took for Chem 50, you may got a lot of that or maybe not a lot of that. So just to make sure everybody's on the same page in terms of how to balance things, we're going to go over kind of some basic balancing redox reactions in acidic and basic conditions. And then we'll get into really the heart of the chapter, which is really about galvanic cells and electrochemistry. And we'll talk a little bit about batteries. And towards the end, we'll talk about electrolysis and what's going on with that. So electrochemistry really does deal with a certain type of reaction, which are what are referred to as redox reactions. And redox reactions are really the big classification of reactions that ultimately deals with a transfer of electrons, typically. And by the way, redox reactions more specifically are reactions that you probably are familiar with. Synthesis reactions are redox reactions. Decomposition reactions are redox reactions. Single replacement reactions are redox reactions. And also combustion reactions all fall under sort of the redox umbrella of more specific ways of classifying reactions. So redox stands for oxidation and reduction. And when we talk about oxidation and reduction, they have a few different meanings that we'll talk about. But for the most part, oxidation typically means that you lose an electron is one definition. And reduction means that somebody gains electrons. Sometimes people like to remember this as Leo the lion goes grr. Loss of electrons, oxidation, gaining of electrons, reduction. Nowadays, people are fond of the oil rig, I suppose. Oxidizing is losing, reducing is gaining. You can put Leo the lion on the oil rig, he'll go grr. You don't have to choose either, and just use both, I suppose, in that case. As we'll see, there's also some other definitions of oxidation and reduction. that actually involve oxygen and hydrogen sometimes. And sometimes those are used when maybe figuring out sort of electrons are a little bit more difficult to see what's going on. So when oxidation occurs, so does reduction. So they always occur together. So if somebody's being oxidized, somebody else is being reduced. It's sort of a transfer of electrons from one thing to the next that's occurring. Now, how do we know when we look at something if something is going through oxidation or something is going through reduction? What we typically look at, as we'll talk about in here, is really what is known as the oxidation state, or sometimes oxidation number, it's sometimes referred to. And when you look at the oxidation state or number, which we will in this chapter and some others as well, it is not necessarily always the charge that you associate with certain elements when you're talking about an ionic compound. So what I mean by that, for example, when we think of, say, chlorine, and we think of chlorine as sort of an ionic compound like sodium chloride or something like that, we think of chlorine as being a -1 charge. And that is true, but if you look at something like chlorine, say in ClO3 minus, which is chlorate, it actually has a plus oxidation state and stuff like that. So when we talk about oxidation states and oxidation numbers, they're not always sort of what you envision sometimes when you're talking about an ionic compound, especially when you're dealing with something that is sharing electrons rather than transferring electrons like there is an ionic compound. So how can you tell if something's being oxidized or reduced? Well, if you're not sure, but you can sort of successfully identify oxidation states and numbers, you could just use a basic number line to help you out. And usually to the right there of zero is positive numbers, to the left of zero is negative numbers. So when somebody gets oxidized, they lose electrons. And when you lose electrons, you then become more positive as you have more protons than electrons at that point. So if you look at the oxidation state or number of something on the left-hand side of the arrow to the right-hand side of the arrow, and it is moving in this direction on like the number line towards the positive numbers, that substance is going through oxidation. Now, if you gain electrons like what happens in reduction, then you become more negative because now you have more electrons than protons. So now you become more negative. So if you look at the oxidation state of something from the left-hand side of the arrow to the right-hand side of the arrow, and it's kind of moving towards the left on the number line near the negative numbers or moving towards the negative numbers, that substance is going through reduction. So, for example, as we will see there, if you took something like sodium and you took some chlorine, and you make a little sodium chloride, right? Maybe a little balancing like I'm in chemistry class here. There we go. So in this reaction, which by the way is a synthesis reaction, which is a more specific classification of a redox reaction, when we look at what's happening with each of these things, when we look at the oxidation state, for example, of sodium metal here on the left-hand side, maybe to the surprise of some people, it is zero. A reminder that any element off the periodic table that's by itself uncombined has no charge. Things only get charges when they hook up metals and nonmetals. That's when those things get charges. So by themselves, they have a zero oxidation state or really no charge. That means also the chlorine over here has a zero oxidation state as well. It's not till those two things come together on the right-hand side of the arrow that they become an ionic compound and actually have charges, which is kind of like their oxidation state. And the sodium becomes +1 and the chlorine here becomes a -1 in that case. So how you could use this number line is very simple. You could go for something like sodium, and sodium started at 0 on the left-hand side of the arrow and ended at +1, which is moving in that direction, which means in this case, sodium is going through oxidation. One of the nice things about redox reactions is if you can successfully identify one thing, like that thing's going through oxidation or that other thing's going through reduction, by default, the other guy is going to be doing the opposite thing. So this guy would go through reduction. By the way, you could still use the number line for that guy. It's chlorine on the left-hand side, it started at 0. and on the right-hand side ended at -1, which means it is traveling in the negative direction, and it is basically going through reduction in that case. Any questions on that there? By the way, the thing being oxidized, the thing being reduced is always found on the left-hand side of the arrow. So that is where you find those things. Now, this also should make sense because that is a metal and a non-metal coming together, which means metals typically gain or lose electrons. Metals typically lose electrons, right? Because of all those periodic trends, non-metals typically gain electrons, which is why they end up being negative, and metals end up being positive. So whenever you have an ionic compound with a metal and a non-metal coming together, you could very quickly identify what's being oxidized and what's being reduced, because the metal should always be the one oxidized and the non-metal should always be the one reduced, because that's what happens when those two get together because of their periodic trends. The metal, because of its very low ionization energy, just gives away its electrons, and the non-metal with its high electronegativity will just pick them up with no problem. Now, this also works great, the number line, in case you have, something like this, for example. Say you got iron 3 on the left-hand side and iron 2 on the right-hand side. Is the iron going through oxidation or reduction? Take a moment and think what's going on here. Okay, so if you're not sure, again, we could look at the oxidation state, which is the charge on ions, by the way, is the oxidation state. So we're starting at +3, going to +2. So if you just go on the number line, say +3 is here, and it's ending at +2, which means it is moving to the left there towards the negative numbers, and this guy is actually going through reduction. Yeah. Any questions on that there? All right. So as I mentioned before, in an electrochemical process, oxidation reduction reactions, the energy released by the spontaneous reaction is converted to electricity. It's used to do some type of work. It is really what happens with batteries. That's basically a redox reaction. It releases those electrons. Electrons go out on a wire, does some work, comes on back to the other side as well. Electrical energy is used to cause a non-spontaneous reaction to occur. And again, sometimes you just apply some extra electrical energy to cause things that normally would not occur. Again, here, if we look at what is happening, magnesium by itself has a 0 oxidation state. Oxygen in its natural state there is going to be 0. Not until those two guys get together, +2, -2. So once again, if you're not sure what's going on, you could take a look at the magnesium starting at 0 and ending at +2, which means it is moving in the positive direction, and that is going through oxidation. And oxygen is starting at 0 in this case and going to -2, which is moving in the negative direction. So this guy is going through reduction. We could actually break apart this overall reaction into what are referred to as half reactions. And when you have a half reaction, you could have an oxidation half reaction and a reduction half reaction. So basically here we have magnesium going from 0 to +2, losing electrons here. And that would be our oxidation half reaction. I know it's an oxidation half reaction because electrons are on the product side, like they are being given off or they are being lost. So that is basically what that means. Here, the oxygen with 0 is picking up those electrons and becoming -2. And this is a reduction half reaction. And I know this is definitely a reduction half reaction because our electrons are reactants, like they were being gained. We always have a balanced number of electrons. And what I mean by that is whoever loses electrons, however many electrons they lose, is the exact same amount of electrons somebody else gains. The electrons in these half reactions should always be the same number. And sometimes that does require you to have to multiply a half reaction by a number, or maybe both half reactions by a number to get them to the same number of electrons. But they should always be the same number of electrons. In this particular case, magnesium, when it loses electrons, because it's group 2, will end up with a +2 charge. And since there's two magnesiums, each one loses 2 electrons. That's how we get to 4 electrons here, right, in our half reactions. 2 from each magnesium being lost. And each oxygen will individually gain 2 electrons, which is why each oxygen on the bottom there will end up at -2. These are obviously called half reactions because, frankly, if you add these guys together, you will get the overall reaction. So if we add these guys together, which you can do, by the way, before you could add them together, as I just mentioned a second ago, you do need to make sure that these numbers are always the same before you add them together. And because they're on opposite sides of the arrow, anything that's on opposite sides of the arrow will cancel or reduce down. So that will cancel and that will cancel. And if you bring it down, that will give us our 2 magnesiums plus our oxygen. These are 2 ions that will come together to make 2 magnesium oxides in this case. So half reactions are pretty much that. They are half of what's going on. One should represent the oxidation and one should represent the reduction. Any questions on that there? Now, another important thing that's sometimes talked about in redox reactions are what are known as oxidizing agents and reducing agents. And the oxidizing agents and reducing agents are a different question than what is being oxidized and what is being reduced. So that is a different question than that one there. So if they talk about the oxidizing agent or reducing agent, the oxidizing agent is actually the substance that gets reduced. And the reducing agent is the substance that gets oxidized. So when we talk about the agents, the good way to remember it is opposite of their name. So oxidizing agent is the guy going through reduction. Reducing agent is the guy going through oxidation. The reason they're called that is if it is the oxidizing agent, that means that it will cause somebody to lose electrons. And because it loses electrons, that will allow it to gain those electrons and it will go through reduction. The reducing agent is a substance that gets oxidized, which means it will lose its electrons, and that will cause somebody else to gain those electrons and become reduced. So the agents basically cause that effect in the opposite substance. In this particular example, since magnesium is the going through oxidation, that would be our reducing agent, in this case, the magnesium. And the oxygen here, which is going through reduction, would actually be our oxidizing agent in this case. Also found on the left-hand side of the arrow. So again, whatever's being oxidized, whatever's being reduced, the reducing agent and the oxidizing agent, all those things are found on the reactant side of the arrow. Any questions on that there? All right, so as I mentioned before, those are our half reactions. We could add them back together again. And basic sort of redox reactions, really the one thing you just got to make sure of is electrons are always the same. May require you, as I mentioned before, to multiply either one or both of the half reactions by numbers to make sure that they cancel out completely. Now, if we look at calcium here, again, with some oxygen, calcium by itself, 0 oxidation state. Oxygen by itself, 0 oxidation state. When these two guys get together, +2 and -2 when we make calcium oxide. And again, if we just kind of slap our little number line together here, we got calcium starting at 0, ending at +2, definitely going through oxidation as it's getting more positive. Oxygen starting at 0 and ending at -2, definitely becoming more negative, which means it's going through reduction. So again, oxidation like we would expect here, since that's a metal. Reduction, which we would also expect here because that is a non-metal. That would mean that my reducing agent would be which one, the calcium or the oxygen? Yeah, the calcium here would be my reducing agent, and my oxygen would be my oxidizing agent in this case. Once again, we could split this up into two half reactions. We see our electrons here on the product side, which tells us this is our oxidation half reaction. And here we see our electrons on our product side, which means this is our reduction half reaction here. Again, electrons will essentially cancel out and give us the overall reaction when we put it together there. So as I mentioned before, the reducing agents are always the substance that gets oxidized, and the oxidizing agents are always the substance that gets reduced. So calcium, as we just saw there, was losing electrons, our reducing agent, and oxygen would be gaining, which would be our oxidizing agent. Now, there is a couple of other definitions for oxidation and reduction, and we'll go over them here just briefly. But truthfully, you probably won't see them too much in our sort of chemistry. But if you continue on to organic chemistry, they oftentimes will be used a lot more than sort of electrons. So as we saw before, oxidation can mean that something loses electrons. It also can mean that something gains oxygen as it goes from reactants to product side, or that it loses hydrogen as it goes from reactants to products. So those are sort of three definitions of oxidation. Reduction has similar definitions. So reduction again means that it can gain electrons. It can lose oxygen as you go from reactants to products, and it can gain H2 as you go from reactants to products. So the oxygen and hydrogen is very commonly used with organic chemistry in terms of oxidation and reduction, and that is because it's much easier to follow what's happening with hydrogen or oxygen rather than trying to figure out electrons, especially in organic chemistry because it deals a lot with nonmetals and nonmetals, carbons, hydrogens, oxygens, and those type of things. So sometimes that is what's going on there. So for example, if we look at our tin substance here on the left-hand side versus the right-hand side. Tin has some oxygen there on the left and no oxygen on the right, which means that it has lost some oxygen as it goes from left to right, which means that it is going through reduction. By default, this guy here would be going through oxidation, but you can also follow what's going on. Carbon has no oxygen, but gains oxygen. So it is going through oxidation here. That would mean the carbon here is our reducing agent, and it really is the tin here that is our oxidizing agent that's happening. So again, if you have more oxygen and hydrogen, sometimes you could look at that. The deal on this particular one is you actually have a metal, so you could kind of follow what's going on with that. You have a -2 here for the oxygen, which means this is tin 4, and over here this is 0. So again, if you look at just tin in this particular case, it's starting at +4, which is here, and ending at 0, which is moving to the negative side, which means it is going through reduction. And if you were able to identify that, you would obviously know that opposite there for the other guy is what's going on with that. Any questions on that there? Okay, so let's talk officially about, again, how to calculate oxidation numbers, which again are sometimes referred to as oxidation states. And this is really important because if you can't do this, you probably might mess up the rest of the stuff that you have to do or figure out what's being oxidized, what's being reduced. So when we talk about oxidation number or state, it's really the charge the atom would have in a molecule or an ionic compound if basically everything was transferred in terms of electrons. Now, as we talked about, pretty much any element that's by itself, not combined with anything else, will have an oxidation state of 0. If you have any type of ion, basically by itself, a monoatomic ion, whatever the charge is on the ion, then that would also be its oxidation state. So lithium with a +1 charge would have a +1 oxidation state, As I wrote earlier, if you had an iron 3 ion just hanging out, then the oxidation state would be a +3. If you have oxygen involved, that's usually the best place to start. Oxygen will have an oxidation state of -2. And the only exception to that would be if it's really not necessarily oxygen by itself, but it's actually peroxide, which is a polyatomic ion, then it would be -1. So hydrogen peroxide, for example, is probably the most common one of that. Sodium peroxide is also another very common one. How do you know it is? Usually because this is O2 minus, there's usually an extra 2 kind of hanging out there on the oxygen, and they're usually on the other element as well to balance out the charge. Oxidation state of hydrogen is +1, except if it comes after a metal like LiH, then that would be the hydride version of it, where it would be -1 in this particular case. Anybody in group 1 will be +1. Everybody in group 2 will be +2. Fluorine will be -1 always. When you add up all the oxidation numbers or state, they do need to equal the charge on the molecule ion. So if it is a neutral molecule, everybody needs to add up to 0. And obviously, if it has an overall charge like -2, like a polyatomic ion, for example, you need to add everybody up to -2. You should also, when you give oxidation numbers or state, you should include the plus or minuses with it. So even if it's positive, you should write +1 or +2, not just 1 or 2. And obviously, if it's negative, you should include the negative with it as well. So if we look at our friend bicarbonate here, and if you have like a 3-pack like this, usually the best move is to go right, go left, and save the one in the middle for the end in terms of applying sort of oxidation numbers. Definitely you have oxygen. That's usually the good place to start. So that's usually the goal here. So we know oxygen is going to be -2 in this case. We also know that there are 3 of them, which will give us really an overall sort of -6 charge based on each of those oxygens. We go to the left, that's hydrogen, which should be +1, which will give us a +1. Now, this is bicarbonate, which has an overall charge of -1, which means when we add these together, we actually need to end up at -1 and not 0 in this case. That would mean that the carbon in this case, I believe, will be a +4 to do that. +1 +4 is +5, and a -6 is a -1 overall, and that would give it. Now, if you're going to give these as answers, hydrogen here would be again +1 is the oxidation state. Carbon would be +4, and oxygen would be -2, not -6. So when you're asked to give the oxidation state or number, it's like just for one by itself, not like the grand total of all of them together for that particular element. So again, don't go -6 for the oxygen. It should be just -2 in that case. Any questions on that there? All right, so why don't you give it a go here? Okay, so let's take a look here. We'll go with our Li2O. So again, here we're going to start with oxygen, which is -2. And since lithium is group 1, it is going to be +1. So lithium would be +1, and oxygen again would be -2. Taking a look at our PF3. Fluorine, again, always going to be -1, and there's 3 of them, which gives us a -3 in this case. And our phosphorus there, since this guy has no charge, should equal 0, so that's got to be a +3 in this case. So the phosphorus here would be +3, and the fluorine would be -1 in that case. Yeah. If we look at nitric acid here, oxygen -2 gives us like a -6 overall for the 3 of them. Going to the left there, hydrogen +1. In this case, nitric acid is neutral, which means they do need to add up to 0. So in this one, the nitrogen here will be a +5. 5 in that particular case. And lastly, we got, and again, hydrogen would be +1, nitrogen +5, and oxygen -2. We got Cr2O72 minus, a little dichromate, starting with the oxygen -2 gives us like a -14 overall by times them by 7. This does need to equal -2 as that is the charge. Here, though, we do have 2 chromiums. So obviously here to get to -2, you would need something like +12. And since there's 2 of them, that means that each chromium is going to actually be +6 in this case to get you there, right? Equals 6, basically. So chromium would be +6, oxygen would be -2 in this case. Any questions on how to assign those oxidation states or numbers? Now, again, you may be thinking, well, for example, when we take a look at phosphorus and we think about phosphorus in like an ionic compound, it's usually a -3 charge. And that is true if it's an ionic compound and you have phosphorus involved and you have a metal, because the metal will give away its electrons. The phosphorus will clearly accept all those electrons and become a -3 charge. It is different in a compound like this. If you quickly sketch it, you got this deal happening here. You also got some non-bonding electrons on top as well, but not really too important in this case. But in this case, everybody is sharing electrons. We are not transferring electrons in this case. And now we have a difference in electronegativity as fluorine is more electronegative than phosphorus. So the electrons that phosphorus has are going to be heading basically towards all of those fluorines. And what that's going to do is going to make the electrons move away from the phosphorus because it's sharing electrons. And it's going to make the phosphorus actually more positive in this case than it would be if phosphorus was on the receiving end of electrons coming in from a metal, which is why it becomes -3 in an ionic compound. But in this case, takes that +3 charge. Also, same idea here, even if you look at, say, nitric acid, something like this. And between the nitrogen and the oxygen, they're in the same row on the periodic table. Oxygen is more electronegative, which means the electrons being shared here from the nitrogen are going to find themselves heading towards the oxygens here. And again, that's going to make nitrogen more electron deficient and going to make it more and more positive here. Again, instead of a sort of -3 charge that you talk about. We talked about chlorine earlier when we talked about sort of chlorine in chloride, which is -1. But if you hooked it up with, say, in chlorate, it looks something like this, also some dots there. But again, between chlorine and oxygen, the oxygen more electronegative, going to kind of suck the electrons away from the chlorine because they're sharing them, not going to be transferred because they're still sharing. And again, that's going to move the electrons away from the chlorine and make it more and more positive, which is why in this particular case, the chlorine -2, -2, -2. Overall, this has a -1 charge. So -6 and -1. So that's a +5 happening in this particular case for the chlorine as those electrons kind of move away as they're being shared in the oxygen. So when we talk about oxidation states or numbers for elements that are sharing electrons in covalent bonds, they are sometimes very different than, what we kind of have in our head and sort of beat into our head these kind of normal charges that all these elements make in an ionic compound. If it is an ionic compound, it'll still be the normal charges they would make. Any questions on that there? So let's talk about balancing redox reactions that are a little bit more complicated. So for example, if we have just a basic redox reaction where you have 2 half reactions, really the only thing you have to make sure of before you add them together is same number of electrons in each half reaction. Again, you might have to multiply one by a half reaction by a number or both by a number. But when we're doing a little bit more complicated and we want to balance redox reactions in either acidic or basic conditions, there's a few more steps that you have to kind of take on once you go through it. So if you had a reaction like this and we wanted to balance it in acidic conditions, the first thing that's probably a good idea is to really figure out what's going on. And what I mean by that is who's being oxidized, who's being reduced. So if we look at the iron here on the left, it is iron 2, which means it has a +2 oxidation state. We just did this guy here, so the chromium was +6, the oxygen was -2. The iron on the right-hand side is iron 3, which means it has a +3 oxidation state, and our chromium here has a +3. So again, if you're not sure, you could go to your number line there to figure it out. So if we look at the iron, iron is starting at +2, which would be about there, and ending at +3, which means it is moving in the positive direction, and that means that the iron here is going through oxidation. If we look at the chromium, chromium starts at +6, which is like over here. And on the right-hand side, the chromium ends at +3, which would be moving in this direction towards the negative side. And that means that the chromium here is going through reduction, or the dichromate in this case. Any questions on how to identify that? Also means in this case that the iron here is my reducing agent, and the dichromate here is my oxidizing agent. And again, really the chromium there is what's happening in this particular case. So once you figure out sort of what is being oxidized, what is being reduced, really the next thing you want to do is split this reaction into the two half reactions. So the easy way to do that is just to keep elements together. So iron on one side, iron on the other side. Chromium on one side, chromium on the other side, yeah? We have already identified this as being our oxidation half reaction, this being our reduction half reaction, right? Now, once you do this, the next thing you want to do is balance all elements. So you want to balance all elements except hydrogen and oxygen. So in this case, on the iron half reaction, I have one iron on the left, one on the right, so it's good to go. Bottom half reaction, I have two chromiums on the left, only one on the right. We balance it like a normal reaction or equation. We just put a coefficient in front, so we do need to balance that. Now that we balanced all of the elements besides hydrogen and oxygen, we then will balance the oxygen. And we balance oxygen in this method by adding water. And we add water to whichever side needs oxygen. Now, the problem with that is when I add water to balance out the oxygen, oxygen is H2O, which means it also is adding hydrogen. So every water that you add to one side, you need to add 2 H pluses to the other side. So one side gets the water to balance out the oxygen, the other side gets 2 H pluses to balance out the hydrogens that you added. So in the case here of the iron, there is no oxygen, so we don't have to worry about it. In the bottom one, there are 7 oxygens, which means the right-hand side will need 7 waters to balance out the oxygen. And because I added 7 waters to the left-hand side, I will need to add 14 H pluses. Otherwise, I will be short some hydrogen at the end. Also, a side note is if you are starting out in your half reaction with more hydrogen on one side than the other, you could just add H plus to the other side, however many you need to balance it out. So you could also, in that situation, kind of just add H plus to start with. Once you do this, the next thing we're going to do is balance out the charge with electrons. And the way that we're going to balance out the charge in each half reaction is we want the overall charge on each side of the arrow in each half reaction to be the same. They do not have to be 0 on both sides. They just need to be the same number. So the easiest way to do this is just to look at the overall charge. Now, some people look at each element and see what's happening with the element, but frankly, that's a waste of time because all the oxidation states need to add up to the overall charge. So if the thing adds up to 0, it's all going to add up to 0 anyways. So you might as well just look up at the overall charge. So on this side here, we have a +2. On this side here, we have a +3. That means that the right-hand side here will need an electron. With 1 electron, that's a -1. That nets me a +2 on the right to match the +2 I got going on the left-hand side. Any questions on that there? If I look at the bottom one, that has 14 H pluses. That's going to contribute +14. This entire thing has a -2 charge, which means it all adds up to -2. That's going to give me a net +12 going on the left-hand side. On the right-hand side, that is 2 times 3 plus, which is +6. And that is 7 times 0, which is 0. So that is +6. Remember that we're adding negative electrons, so you need to add it to whichever side needs that negative number. And in this case, you actually need 6 electrons over here. That's going to give you a -6, and a +12 is a +6 on the left to match my +6 here on the right. Any questions on that? By the way, by identifying what is being oxidized and what is being reduced, you can make sure you did this correctly. Since this is the oxidation half reaction, those electrons should be on the right-hand side, which they are. And since this is a reduction half reaction, those electrons should be on the left-hand side, which they are. You should never, ever add electrons to the same side because you definitely are screwing it up for sure. So they should always be on the opposite sides of the arrow. And again, identifying what's being oxidized, what's being reduced, you could make sure you're at least adding them to the correct side. Or before you even start, you'll know which side you should add the electrons. So it makes it a little bit easier as well if you know what's being oxidized, what's being reduced. Any questions on any of that there? All right, we're almost ready here. So the next thing you do after you balance out the charges, you're almost ready to add everybody together. I'm just going to erase some of my scribble here so we can kind of see what's going on here. So the next thing we want to do is actually add these together. But before we could add them together, the one thing that we always need to make sure of is that we do have the same number of electrons on both sides of both half reactions. And in this case, we do not. On the bottom here, we have 6. Top one, we have only 1. So we will need to multiply, in this case, just the top guy by 6 so that we could have the same number of electrons in each. I'm just going to rewrite it underneath. That will give me Fe2 plus, and I should have 6 of them, going to 6 Fe3 plus and 6 electrons. So again, all I did is just distribute that 6 to everyone, not just the electrons. At this point, we do have the same number of electrons. So now we can add the half reactions together. We could cancel out the electrons, which should always completely cancel out. And anything else that's on opposite sides of the arrow, you could either cancel out or reduce down. So in this case, it looks like it is just going to be the electrons that are going to cancel. Everybody now on the left-hand side of the arrow stays there, and everybody on the right-hand side of the arrow will stay there. That will give me 14 H pluses plus Cr2O7 minus plus 6 iron 2s go to, on the right-hand side, 2 Cr3 plus 7 waters and 6 of the Fe3 plus. Now, if I did not screw up, 50-50 chance, this should be balanced here 2 ways. It should be balanced like a regular equation, which means you have the same number of elements on each side, and it also should have the same charge on each side. So let's see. Over here on the left-hand side, we got 14 H's. It's got 14 H's there, so that's good. 2 Crs, 2 Crs. I got 7 oxygens there, 7 oxygens there, 6 irons there, and 6 irons there. So that is check. We're good We got the right number of elements on each side. Overall charge on the left, that's going to give me a plus 14. This entire thing will give me a minus 2, and 6 times 2 is plus 12. Dare I say that equals, not 0, I was hoping, but it doesn't. It actually equals a plus 24. Did I get that right there? I feel like maybe I messed that up, but I think I got it. So that's a plus 24 there. On right-hand side, we got plus 6, we got 0, and we got a plus 18. 18 and 6 is a plus 24. So balanced in terms of charge on each side does not need to equal 0. Just needs to be the same number on each side. And in terms of elements, any questions on that there? This would be balanced in acidic conditions. Can you take a guess as to why I know this is balanced in acidic conditions? Yeah, we see H plus, yeah. So we know that this guy is balanced in acidic conditions, yeah. Any questions on that there? All right, we will stop for